picking up good vibrations.
Hi, today we're going to talk about complex numbers, which are very important for signals. And we're going to talk about sum and multiplication of complex numbers, polar coordinates, of the polar form, complex conjugates, sum of geometric series, complex signals, derivation, integration, fundamental theorem of calculus. Now, this is mostly to recap these concepts, as you should know this already. We'll start, however, with some motivation. And the main motivation to consider complex numbers for signals is that the very important signals, which are cosine of omega t for a given omega and sine of omega t, can be written as the sum of complex exponentials. So if we have, for instance, cosine of t, I can write this as e to the power of jt plus e to the power of minus jt over 2. Now, this formula helps us in many, many ways. You probably already know that if you want to multiply two cosines, for instance, say cosine of t times cosine of 3t, this would be very hard to do if you don't know anything about complex numbers. But if you do know, it's just a matter of replacing this expression, number one here, in these two expressions. And after some derivations, you can conclude the formula that I know by heart, which is this one, very easily. Pretty much as we can do this type of operations with complex numbers, in signals we can also do a lot of other operations in a much easier way. And finally, in the context of signals, we know that if we have as input to an LTI system a cosine of a given frequency omega, the output will also be a cosine by multiplied by a given amplitude and shifted by a given phase phi. This is quite straightforward already, but it's even more straightforward if we have as input to an LTI system a complex exponential, a given frequency omega. We will understand that the output will be a given complex number, let's call it z, e to the power of j omega t, where j has a given amplitude a and a given phase phi. Now, you might be wondering if we could live without complex numbers. Yes, we could, but this sort of operations would be much harder. We'd have a much more cumbersome theory, and that's why we use complex numbers. Another reason, of course, is that everyone else in the world uses complex numbers, and that's also why we're going to follow this framework here also in this course. So let's start with sum, multiplication, and polar coordinates. Suppose that we have a complex number z equal to x plus jy. So j represents the complex number, which, as we know, is the square root of -1. It doesn't exist, so that's why it's a complex number. And we can say that j squared equals -1. So we can represent this complex number z in the complex plane. This is the real part of z, which is x. And then we have the imaginary part, y, here. Now, if we want to add, if we have another complex number, w equals u plus j v, say that we have here z, and this is w. If we want to add these two, it just amounts to adding the real and the complex part. So if we call y a to be z plus w, this is nothing more than a complex number with real part x plus u and imaginary part y plus v. Geometrically, it amounts to simply adding these two vectors over here. Now, this is the sum, we can also define the exponential of a complex number. So the exponential of z is by definition e to the power of the real part times cosine of the imaginary part plus I plus j e to the power of the real part times sine of the imaginary part. Now, if we want to multiply two complex numbers, that's a little bit more tricky. We can apply the operations, or we can first transform those two complex numbers into polar coordinates, and afterwards do a much simpler operation. So what are polar coordinates? For instance, for z, I can consider this distance over here, rho, and call this rho to be the square root of x squared plus y squared. And then I can say that simply x is nothing more than rho times cosine of theta, where theta is this angle over here. And I can say that y is rho times sine of theta. So basically I can write z as, looking at the formula that we have here for e to the power of z, I can write z as rho times exponential of j theta, which is nothing more than rho times, using this definition with x equals 0, cosine of theta plus j sine of theta. So let's say that we have two complex numbers, z equals rho 1 e to the power of j theta 1, and then we have w equals to rho 2 e to the power of j theta 2. If we want to multiply these two complex numbers, it's as simple as multiplying the absolute values and adding this phase or angles. As simple as that. So it's much easier to first convert to polar coordinates and then just apply this multiplication. So now let's move on to complex conjugate. If we have a complex number, x plus jy, its complex conjugate, denoted by this, is nothing more than x minus jy. So if we plot again in the complex plane z, this is the imaginary part, this is the real part, the operation of taking the complex conjugate of a complex number j is nothing more than a reflection about the real axis. Because then we can write x minus this is minus y, and this is nothing more than x conjugate. Now, if we write this z as with polar coordinates, it's polar form, so this is theta, and this is rho. Theta is the angle in the anti-clockwise direction with respect to the real axis. Taking the complex conjugate is nothing more, the absolute value stays the same, geometrically is very easy to see, and the angle changes sign. So now we have z conjugate equals rho e to the power of minus j theta. So there's a few properties around this. The first one is that if we add z to its complex conjugate, we get 2 times the real part, x. And that implies that if I want to take the real part of z, it's nothing more than z plus z conjugate over 2. If we want instead the imaginary part, this is nothing more than taking the difference between z and z conjugate, and this leads to 2 times y. And this implies that 2 times jy. This implies that the imaginary part of z is nothing more than z plus z conjugate over 2j. If we want to take the product of z and z conjugate, we'll get in polar coordinates e to the power of minus e to the power of j theta times rho e to the power of minus j theta, and this will cancel out with this, and we get rho squared. Finally, if we want to take the inverse of z, this is, we can multiply the numerator and the denominator by its complex conjugate. It's equal to this. We can use this property here to say that this is rho e to the power of minus j theta, that's the complex conjugate over rho squared, and this cancels with this, we get 1 over rho e to the power of minus j theta. So now we're going to look at the sum of a geometric series. So let's say that we want to add from k equals I until L, z to the power of k. So the formula is very similar to the formula, actually it's the same formula that we have in the real case. When z is real, let's say z is complex. And it's given by this. Is the first one, z to the power of I, minus the one that we haven't added, zl plus 1. The last one plus 1, 1 minus z. And the way to see this is exactly the same as in the real case. We can just basically notice that the summation is equal to z to the power of I plus z to the power of I plus 1 all the way to z to the power of L. And if we multiply by 1 minus z, and the numerator and the denominator, and z here must be different from 1. If we do that, we will get that we'll get zi plus zi minus minus zi minus zi plus 1 plus this times this, which is zi plus 1 minus zi plus 2. This will cancel. This will also cancel with the next one until all the way to z. I multiply this by this, I get z to the power of L minus z to the power of L plus 1. This will also cancel with 1 in between, and this will stay. And then I cannot forget to divide by 1 minus z, and if I clean up this a little bit, I'll get the formula that we've just seen. Now, an important special case happens when I consider I equal to be 0, and I let L go to infinity. So this will be equal to 1 minus z L plus 1, 1 minus z. And when I take the limit as L goes to infinity, if I say that the absolute value of z is less than 1, then z to the power of L plus 1 will be its absolute value, e to the power of j theta times L plus 1, its phase, to the power, absolute value to the power of L plus 1. And then if I let L go to infinity, if the absolute value is less than 1, you see that this will converge to 0. So this term will cancel, and this limit will be 1 over 1 minus z. Let us now talk about complex signals. Pretty much like we define a complex number as a real number plus j real number, a complex signal is nothing more than a real signal plus j times a real signal. Now, by far the most important signal that we have for our course, complex signal, is e to the power of j omega. Omega is a constant times t. And it's nothing more than cosine of omega t plus j sine of omega t. Now, typically, we pre-multiply this complex signal by a given complex number. Let's call it A. And if A is a complex number with a given magnitude or absolute value, rho e to the power of j theta, this will be nothing more than rho cosine of omega t plus theta plus j rho sine of omega t plus theta. So this complex number tells us the amplitude of these sines and cosines, and also the phase in just one. It's summarized in one complex number, and this is called the phasor. So now, derivation and integration. If we have a signal z of t equals x of t plus j y of t, we define the derivative of z with respect to time t to be the derivative of the real part. So the real part of the derivative is the derivative of the real part plus j, the derivative of the imaginary part. So the imaginary part of the derivative is the derivative of the imaginary part. Suppose that we have the signal that is clearly the most interesting for our course, e to the power of j omega t. Omega is a constant, is fixed. Now we want to take the derivative. We can apply this to say, well, I know that this is nothing more, the real part of this is cosine of omega t plus j sine omega t, that's the imaginary part. If I want to take the derivative of this, I can simply take the derivative of the real part, which is minus omega sine of omega t plus j, the derivative of the imaginary part, which is cosine of omega t. Now, we can write this in a different form. If I just factor out this term here, I'll get j omega cosine of omega t plus j sine of omega t. Because when I multiply j omega times j, I get minus omega. But this is nothing more than e to the power of j omega t. So we're left with j omega plus e to the power of j omega t. And basically this leads to a very simple generalization of the differential rule also for this complex function, which is if we have e to the power of j omega t, the derivative is j omega e to the power of j omega t. So this term here moves out when we take the derivative. We can also define the integral of a complex signal, integral from a to b of zt dt to be the integral from a to b of the real part plus j, the integral from a to b of the imaginary part. Now, we have just seen the definition of a complex of the integral of a complex function. But here in the complex domain, we also have the fundamental theorem of calculus that tells us that if we want to compute directly this integral, if we know a function, let's say wt, whose derivative is z of t, then this integral is obtained by evaluating such a function at points b and a. The integral from a to b of this complex function z of t equals wt, which is the primitive, evaluated at b and a. Now we can, for instance, consider the integral, consider an example where we want to compute the integral from 0 to 1 of e to the power of j to t. We can use formula number one, the definition to arrive at this is nothing more than the integral from 0 to 1 of the real part of e to the power of j to t, which is cosine of 2t, plus j dt, plus j, the integral from 0 to 1 sine of 2t dt. Now, the integral from 0 to 1 of cosine of 2t, we have to take the primitive, which is 1 over 2 sine of 2t evaluated between 0 and 1, plus j, the primitive of sine of 2t, cosine of 2t over 2, evaluated at 1 and 0. And if we do that, we get 1 over 2 sine of 2 minus 0 plus j minus 1 over 2 cosine of 2 minus here plus 1 over 2 times 1. Now we can use the other formula. We can compute it with the fundamental theorem of calculus for complex signals or functions, and we can try to figure out a function whose derivative is e to the power of j 2t. And since we know that if we try out this one, j 2t over t, if we make wt to be equal to this, we know that once we take the derivative of wt, sorry, this is 2j, this 2j will cancel out and we'll get z. So this is the primitive. So we can just simply use this primitive, e to the power of j 2t over 2j, evaluate at 1 and 0, and this gives e to the power of j 2 minus 1 over 2g, which is cosine of 2 plus j sine of 2 minus 1 over 2j, which is nothing more than 1 over 2 sine of 2 plus cosine of 2 minus 1 over 2, and 1 over j if I multiply the numerator and 1 and the, so if I have 1 over j, if I multiply and divide by j, I get j over minus 1, so it's minus j. So here I'll put a minus j here. And as you see, this coincides with the formula given here.